I don't normally go around giving talks in suits. So if you're wondering why I'm this formally dressed, just picture me wearing a snail hat this entire talk. Okay? Cool. So the thing I'm giving a talk on is what explanations we want out of interpretability. So broadly, I'll just be talking about like what does the field of interpretability exist for, like what kind of guarantees do we want out of like interpretability methods that we develop, and so on and so on. So generally, the outline I cover will be this. I'll talk about like what the general answer is to like what kind of things we want out of interpretability, and then I'll talk about like what specific components do we want out of specific components of a model do we want to interpret, or would we want to explain given our interpretability methods if we don't want like a fully ambitious answer, and or like, well, in another frame, how much of our model do we need to explain? And then I'll go into a bit on like how current approaches handle this, like perform on some of these metrics. Then I'll talk about like basic taxonomy for like thinking about interpreting methods and like what kind of purpose they each serve to achieve. And then I'll talk about, well, what I'm working on right now, which is what I call high-level interpretability. This is a talk I've been meaning to give for a while now, and it's the first time I'm giving it. So I'm pretty sure that like there'll be a lot that's like not very well presented here because it's like a pretty dense thing that I've been thinking about for a while. So if you guys have any questions, feel free to interrupt me during the talk and just like ask them anytime you have the questions. I generally prefer like a more free-flowing style that way. Cool. So the general and ambitious answer to what we want out of interpretability. We want a language that lets us robustly map model internals to their equivalent human understandable things in the real world. And what I mean by that is that we want something that lets us that we want some kind of framework that lets us take like whatever it is that we're looking at within a model and say, okay, this is what this maps onto in the real world. In the really ambitious sense, this basically gives us some kind of like, well, language in a fully general sense. You can think of it in the CS theoretical sense. So some kind of language that lets us like say, this is some mathematical thing that like the network is using, and these are its equivalent bindings in the real world that they map onto. And this is like a really ambitious thing to want. It basically like, in full generality, it solves the ontology identification problem in alignment. And yeah, if you try to do this the naive way, you basically run into a bunch of problems where if you try to do this the way the standard mech-interp tries to do this, you run into problems with, okay, I'm going to reverse engineer this particular component of the circuit. I'm going to look at what this attention head is doing, and then you discover, it's like representing the information corresponding to like the country of France or something. And then you discover, it's also doing like these 5 other things. And then you like try and like figure out, okay, so what exactly is representing the things I care about in the real world? And they have to like look at different layers and different heads and like figure out exactly what across these different layers in a very sparse way corresponds to the things you care about. And then you run to a bunch of like weird combinatorics problems. Implicitly, like the problem you want to solve here is there are things you care about, and there are things that like those things are really value laden and complex, and they're not going to be like represented in a really easily identifiable way in the model's network or ontology because there's no real reason for them to be represented that way. And so you need to solve a really hard problem that looks like, here are the things I care about, and here's the generalizable form in like basically any ontology that you care about. And also, I'll be going pretty fast during this talk, so I strongly recommend if you have questions, you just like really interrupt me at any point. So let's try relaxing some constraints, because that's definitely a really hard problem to solve. Like there is like this kind of thing, the only research agenda that actually tries to solve this problem in full generality is called natural abstractions. It's what this guy called John Wentworth works on. And I respect John Wentworth a lot, but I think what he's working on is ridiculously hard. But like, it's definitely the kind of thing that would try to get this. John Wentworth tries to come up with like a theory of abstractions in the real world, which basically lets you like figure out what kind of representations are natural to represent, what kind of representations naturally represent information in the real world and represent information within learned systems within that environment, and figure out a fully general way to map between the two. And that like, if it works, you definitely can do the kind of thing where like you can take abstractions within a network and find out like what abstractions they correspond to within the environment. That's really hard. So if you try relaxing some constraints here and just like try to make the problem simpler for ourselves, what are some ways in which you can do this? The first way is, what if we can like only try to map to like some specific things that we care about? What if you don't need a fully general solution to this problem, where you can just be like, okay, so there are some very specific things in the real world that I care about. For instance, I care about whether the model in front of me is deceptive. Can you figure out how to map like specific parts of your model to these specific alignment relevant human concepts? And that's, well, some approaches try to do this. Eliciting latent knowledge is like probably the gold standard for like something that tries to do this, where you like try to figure out like what the latent knowledge within your model is, or like what knowledge your model honestly believes in some sense about the world, independent of what answers it gives you, and try to figure out like how to extract that information in a fully robust way. Also, high-level interpretability is what I work on, just basically the idea of like figuring out mechanistically what objective the model is trying to get at. So in both of these cases, you try to map specifically the parts of the network that you care about onto like the components that you care about. This is definitely really, really hard because it requires that you it requires that you figure out exactly how to interface with only these aspects. But it is a very, very mild relaxation in that you don't need to have a fully general solution to translate like things in the network to things in the real world. But it's not a really good relaxation. Another relaxation could be if you don't need to solve for the mapping yourself, but you only had to like derive some very specific properties about it. So like you've managed to find some way to construct an explanation of the things happening inside your network, and you can say, okay, I don't understand this explanation in any real sense, but like maybe I can like derive some kind of guarantees from like its structure in some capacity. The one research agenda that most closely maps this description is mechanistic anomaly detection, which is like what Paul Krishan is working on right now. This ties into another thing he's working on called heuristic estimators, which is basically a way to like come up with an explanation of what a neural network is doing that like captures all of the information that's relevant to us at a particular level of abstraction, and such that like it can detect when the mechanism a model is using to solve some task changes. And as an example, you can think of this like a model originally is answering some questions honestly, and then suddenly like during training it becomes much more competent and realizes that it's like it can get much better loss if it just like it has a much easier task if it just like tries to answer questions based on what it thought a human would accept as a believable answer. And that's like an instance of like when the mechanism within the model to solve some particular task changes. So in that case, the like mechanistic anomaly detection is the kind of thing that like you don't understand the explanation, but you can detect when this kind of explanation of mechanism happening inside the model changes. So in that case, you don't have to understand the mapping yourself, but you do have to like have the ability to infer some specific properties about it. This is also a relaxation in some sense. It's not like a super good relaxation. In fact, it's still a really, really hard problem, but it is a relaxation in some sense that you do have like a somewhat tractable problem in front of you. And a different kind of like relaxation is just, I'll probably skip ahead too. Yeah. The right kind of principle basis, where like you don't need to understand like a full generality of what your model is doing. You just need to like figure out like the right basis to look at your model in. And I don't know if any of you know what like SAEs are, but like show of hands, how many of you know what SAEs are? How much time should I spend explaining what SAEs are? Some of you don't. I'll just basically explain it. Like a very quick summary is just like if you try to like reverse engineer features within neural networks, you find that like a bunch of stuff, like generally speaking, like features in neural networks are represented using superpositions, such that like if you look at a particular thing, it's probably going to encode like 5 different things at the same time, depending on context. One of them will be like activated, and so you really, really want to like be able to split them out and look at like individual things. So SAEs are a way of like extracting out these things from like superposition. And some people claim that like, yeah, this is finally the right thing we need to do to solve interpretability. You can finally look at like all the individual things your model is doing. This isn't like exactly the right kind of principle basis you want to look at though, because like the things you care about aren't going to be like easily represented within like all the SAE features that you find. Like for instance, if you find like your model has a deception feature, it doesn't really tell you much about whether the model is decepting, whether the system is modeling someone else being deceptive, or whether the model itself is being deceptive. It doesn't give you like much human understandable information about like in what context these activate, or like, or more generally in like it doesn't solve the non-trivial problem of like how are these things being used and how do these things like map onto the more higher level complex things that I care about. The right kind of principle base would basically take like the fundamental computational units of the network and figure out like how to combine those things to like tell you more relevant things about the model that you care about, like more robust explanation, more like informative explanations. I don't know if any of you are familiar with Lucius Bushnack, but he has some prior work on modularity that tries to do this, where he tries to come up with like what are the actual fundamental units of computation in a neural network, such that like given those, you can like arbitrarily combine them together to give you like higher level explanations that you care about. And that's the kind of like work that would go into like coming up with the right principle base. It's definitely a highly non-trivial problem. Also, I'm very surprised that none of you have questions so far, because I've been speaking at a very fast pace. So I'm just going to take a drink for a second. So if any of you have questions, you should probably ask that now.
Yeah, just to clarify, is a principal basis just like a set of features that you see activate that can explain, like, I guess, like, yeah, just like they're linearly independent of explaining features of the model?
Not exactly. So I'm definitely like using the term principal basis in a slightly different way than McInterp generally uses it. It's just the best term I could think of. So when I say principal basis, I mean what is like the framework in which you can view what your model is doing, such that like everything that you see as like fundamental actually does correspond robustly to like things that the model is doing. By that I mean like If you try and look at like a lot of current McIntyre work, for instance, there was a copy suppression paper from like a while ago that basically said, this attention head is clearly doing copy suppression. That's like this token is present in the context window, is going to suppress it when it shows up again to not like prevent copying from showing up. If you try and like look at this, it really recovers like 30 to 40% of like the actual loss that's the actual performance that's like exhibited by this attention head. So it's the kind of thing where if you're looking at the attention heads in a sort of like skewed way, where like these explanations you have of what this model is doing or what this particular component is doing doesn't exactly capture what it's doing. And such, so if you the right way to do this would be some way to look at what the model is doing, such that whatever explanation you back out actually does robustly capture everything that's happening there. So it's like it's sort of a like weird concept to like try and capture, but like principle basis is the best term I could come up with for it. Like what kind of like way can you view the model in, such that like any behavior you see out of it or any like mechanistic processes you understand, you back out of it, actually do robustly capture everything in it. Like SAE is like one example of how, where you won't exactly be able to capture all the relevant like cognitive information that's present inside the network, but like maybe there are other things that are more relevant. Modularity is one instance of like something where like if you actually do look at the whatever results of modularity tell you, you would get everything you wanted out of it. Does that answer your question? Yeah.
So how do we know that this problem of mapping to like deception is easier than the original problem?
One intuition here is that like the general problem requires that you have like be able to solve a many-to-many mapping. It's basically like any arbitrary combination of things within your network. You have to be able to translate like map to any arbitrary amount of things in the real world. There's a in the case of deception, it's a more restricted problem of you have to be able to translate any set of things in the network to this very specific thing that exists in the real world. And like it's not exactly, I don't have like a robust answer as to like, I don't have like very concrete answer as to why like that would be easier, but it's definitely a relaxation in terms of like you don't have to like solve for every possible thing in the real world this could map to. Like there are definitely more complex things in the real world this could map to. Like if you try to solve for like is the model agentic, you'd have to solve like questions of like what does it mean for a model to be agentic that you then have to answer before you can do that in the first place. Deception is like also runs into a bunch of these problems, but it's a more straightforward problem that doesn't require routing through stuff like that. Which what do I say? Yeah.
Okay.
Any other questions? Yeah.
I remember reading a post on this one that described a lot of like the later representations of different features like deception, like how deceptive it is, or like linear nature. Does that still hold up to current research?
Wait, say that again.
Like the level of like some model output, like in the latent space, the representation for some like whether how sad the model will act or how deceptive it could be, were like almost linear in terms of like the latent space. Does that hold up today?
I'd say that like. So it holds up in as much as that there definitely are things that like the model is doing that are represented linearly. Probably the best example I can think of this comes from the Othello GPT paper, where the original paper tried to like discover whether or not the model represents like black and white as two different like as like linear representations within the model. So I mean, you try to back it out using linear probe, you really can't. And the original paper said that you needed to use non-linear probes to back out whether or not like a player is black or white, like black or white feature. And then Neil Downer came in and said, oh wait, you that is true, but also if you just like try to turn a linear probe on, are you the player or is the opponent the player or something to that effect or something, you can actually recover it using a linear probe. So like there definitely are like functional equivalents of a bunch of things that are represented within the model linearly, but like in as much as like things you care about like really validated and they're like highly like specific, if you want to like figure out exactly what those are, like it's a much stronger assumption that those things will be represented linearly as well. Like this is one example of a thing where like that like one instance of something that we cared about wasn't represented linearly. And so like yeah, it becomes more of a question of like, are you trying to like recover something within your network that broadly matches what you care about? Are you trying to like come in with like very specific prescriptive things of what you want to identify? Yeah. Any other questions? Okay. Moving on. Yeah. So we're on to the question of like, when we do all these relaxations, we're basically asking one kind of question. If you don't want to like solve for explaining literally everything within your network in full generality like natural abstractions tries to do, or like sort of, what do you need to explain? Like there are specific parts of our system that we care about explaining. For example, whether they're deceptive or whether they're agentic, whether they have situational awareness. Like a bunch of these questions are the things we really care about asking about our models. And these are also like very non-trivial problems to questions to answer. In fact, like this requires answering a question of like, what does it mean for a model to be deceptive? What does it mean for a model to be agentic? What do you mean by situational awareness? Because for instance, if you want to like figure out whether a model is being deceptive, you need to ask yourself, okay, what part of the system would tell you whether or not it's being deceptive. Like, you can't just simply go around searching for a deception feature, because like deception in general is like, it doesn't have to be something the model is explicitly representing as like, I'm going to now deceive this human. It could just be like some set of actions the model is taking because it thinks that those will lead to like good outcomes in the real world relative to itself that route through deceiving some human about something. And so like, if you care about deception, you need to solve a very non-trivial problem of like figuring out what parts of your system would be relevant to deception. This is a really, really, really hard problem to like solve in full generality in a way that's like robust to a bunch of optimization pressure. There are easier versions of this, like what is the objective of your model such that like you can interface with those things, but that still requires that like you solve like non-trivial problems about like how to robustly identify objectives. Eliciting latent knowledge is an example of like how hard this problem is for the specific case of like truth representations, and CCS is an example of like one instance where you try to bypass all that difficulty, and then you discover that like, oh wait, the problem is actually just very difficult. You can't just like get around it, and the solution won't generalize very well. And yeah, you have to be like, this is the kind of thing that you'll be really, really careful with, because like you could be very descriptive like CCS was by saying, okay, this is like one very specific notion I have of like what has to be true about like truth representations, and that like I conjecture is a necessary and sufficient thing to describe the truth representations with the network. And then you realize that, oh wait, it doesn't like work on literally anything else except the model I looked at. It doesn't work in like other settings. It doesn't really even replicate very well. There's also like other problems with like picking the wrong ontology, and what I mean by that is like picking the kind of thing where, well, Rome is probably the best example of something like this, where there was a paper from a couple of years ago called Rank 1 Model Editing. Well, that's not the name of the paper, but like locating and editing factual associations in GPT, where they tried to edit the model's knowledge of like where the Eiffel Tower was from to change it from like where something to Rome, and see how well that worked. It does not really very robust, and the kind of ontology that you want to operate in would have like discovered, oh yeah, this information isn't going to be represented very locally anywhere, and you do need to like solve for exactly where you want to edit it, such that like you actually are robustly editing it now. And if you try to do this a very descriptive way, or pick the wrong ontology and say, oh, this is definitely going to be represented linearly and locally, then you don't get anything that generalizes at all. And you can also miss like entire surfaces of attack. Like if you simply say, oh, deception definitely has to be something the model is thinking about internally, and then you make sure that your model never thinks about anything deceptive at all. One trivial outcome is just that your model like just optimizes something because it thinks it's competent, because it thinks it's like really good at achieving some outcome, because it routes through like deceiving humans in the real world. One example here is like if you train a model to like output protein recipes and send them to a wet lab or something, and you also have it like output explanations as to here is why I think these recipes will be safe, and then like you make sure the model can never think anything deceptive, and you optimize it to like get past human review really quickly. Eventually, it stumble across the outcome. Maybe I should just craft these recipes and explanations to look this very particular way that just gets me past the review process really quickly. And it does that because humans buy these explanations really quickly, and they have no real binding to truth. So the model definitely doesn't have to like explicitly say, oh yeah, I'm going to deceive these humans now. That's to have the net outcome of deception in the real world. So you want to be really, really careful about like trying to do things like this. Yeah, basically that. I don't know if any of you know what causal scrubbing is. How many of you know what causal scrubbing is? Okay, causal scrubbing was this work by Redwood Research from a couple of years ago that basically tried to show, okay, given this hypothesis about, given this specific hypothesis in interpretability, we conjecture that like this particular part of the model is responsible for this behavior. We then like try to, well, sort of like figure out like how much loss can be recovered, by how true that hypothesis, I guess, is like the high level answer. How much like loss can be recovered if you like assume very strongly that like this specific part of the model is like the only thing that's responsible for it. We're building a sort of informal computational model of like everything the thing the network is doing. And the overall result was, wow, most interpretive methods really do not work very well. And if you try to do this, you will recover like basically very poor performance from your model, because most interpretive hypotheses are not very good and specific. Like the best hypotheses are the ones that are like pretty trivial and cover basically the entire network. And that's why Redwood Research gave up on working on interpretability a few months after that, because they realized that, wow, interpretability is much harder than than we thought, because causal scrubbing shows that most interpretability work is like making a lot of really questionable assumptions, and if you try to benchmark that in any way, you break a bunch of stuff. Okay. Yeah, so what is the alternative here? Like if you don't want to like figure out how to come up with specific hypotheses such that you're like, okay, here are like, so if you don't want to answer the question of how do we answer specific questions about the network, what's the other thing you can do? What's the standard thing that MECINTERP does? It's generically explain like a large fraction of what the system is doing. This is basically what a bunch of MECINTERP work tries to do, like reverse engineer basically everything about the network and say, okay, we reverse engineered like 50% of the network so far. We reverse engineered something that captures 50% of the loss, and that's a great thing because now we can discover 50% of everything the model is doing. And that's like a bunch of hopes around MECINTERP, that you can simply do this with the network and figure out a bunch of stuff. But then the question remains like, how much do we need to explain about the network before we're confident about anything that can happen? And well, I think the standard answer to this should be that like, I think the standard answer should be the explanations and loss aren't really like a one-to-one, such that like you can say that if you have an explanation that like captures 50% of the loss of your model, you can say, okay, I'm capturing 50% of everything that's going on inside my model, and I can't find anything really bad. This is pretty great. And I say that this is definitely not the way you should be thinking about it. In fact, you should be thinking about it in a much more skewed way. Like you should be thinking about it in the sense of like a 50% explanation probably captures like 99% of the loss. And intuition pump here is that like, if you capture like 98% of the loss of a model that's GPT-4 sized, you basically get a model that has 98% of the loss of GPT-4, and that's effectively like a GPT-3 size model. So if you're not worried about GPT 3.5, then explaining 98% of the loss of GPT-4 won't get you anything that's like worrying about GPT-4. Obviously, nothing is worrying about GPT-4, but the intuition is generalizable to like, if you're not worried about GPT-5 and you explain GPT-5 level performance in GPT-6, then you're not really explaining anything that's concerning about GPT-6. These numbers all come from Ryan Greenblatt, who I'm very grateful to for doing all of this math. But like, yeah, so the point being that like explaining 98% of GPT-4 doesn't tell you much about like what makes GPT-4 much better than GPT 3.5. And though that difference in capability on the margin is the thing that you really, really care about. So if you want to explain something, you probably want to explain like 99% of your model. You want an explanation that recovers 99% of the loss or more. And this is really, really hard. Current MECINTERP is much more descriptive than this and just tries to say, oh, in this current context, this induction head, this attention head does this thing, and therefore I'm really confident about this. And it's extremely, extremely bad at this metric. Like I mentioned earlier, the copy suppression paper is one example of this, where they try to limit the copy suppression attention head to only do copy suppression, and it basically has like 30 to 40% of the loss. And you might think that, oh, this is pretty great. You can recover like 30 to 40% of an explanation. But if you compare it to like metrics like this, you realize, oh, wow, this captures basically nothing of what I'm interested in. And this is true for like most current MECINTERP work. Okay, another slide. So any questions so far? Or do you want me to slow down? Do you want me to not slow down? Okay. Really, no questions. Fascinating. Okay. So now let's just dive into a couple of specific ways in which current interpretability method or current approaches to like model internal stuff generally like runs into a bunch of these problems. So I'm going to here define mechanistic interpretability specifically as bottom-up reverse engineering, which is basically like all of the things that Anthropic does. Most of the things that like you generally associate with Chris Sola or Neil Landa. And I'll jump into like how mechanistic interpretability fares in some of these. So most people working on mechanistic interpretability are really, really excited about sparse autoencoders, which are SAEs. And they're like, oh, this definitely gives you a really, really principled basis to operate in. And this gives you like all the information you need about like all the features that the model is activating in. And this will give you like deception features in the model. And it's going to tell you whether the model is deceptive and like a dozen other things. But like it really, really isn't enough for like a bunch of the reasons I talked about earlier, because the things you care about don't have to be represented as like features within the model in like a linear way, in a clean linear way. Go for it.
So the final layer, final classification layer is linear.
Mm-hmm.
So wouldn't that mean that the final layer embedding all the features have to be represented in a linear way?
Yeah, and
Yeah, that's what I'm like trying to argue that SAs wouldn't capture it.
oh yeah, I think there are like other reasons as well, but yeah, if I understood you correctly, I think that's like probably also true. I think if I understood you correctly, yeah, I was thinking that you're going to like distribute my points. I was thinking interpreting a statement in a completely different way, but like if I'm understanding you correctly, I think that's also true. Yeah, yeah. So yeah, SAEs really, really aren't like principled enough, because even with SAEs, like you're talking to most people, they tell you SAEs will be enough to like get you a lot of the way. Like they'll get you like 90% explanation of the model of what it's doing. Some people who really work confident tell you, oh, it'll explain everything what the model is doing. And like this is really overconfident, because most current mech-interp work, even with SAEs, are definitely very descriptive. Literally look at like what a model is, what a specific component is doing, and then you back out what you expect it to be doing in context, and that's like a much more like, that's not like really how that you should be doing like a science of interpretability. You shouldn't be like looking at a thing and like saying, oh, this is what I think it's doing. Like you need a much more robust benchmark here. But the right kind of basis, like I said before, would allow you to build up more complex dynamics to capture stuff like deception. I'm just now realizing that I already said this stuff earlier. But like, yeah, this is the like if you have some kind of solution to modularity where you basically do have the right kind of basis, it would allow you to like actually look at these things and the outputs of whatever tools you have and say, okay, these things make sense to me, and these things combined with these other things that make sense to me in a way that makes sense to me, and say, okay, the model now is being deceptive. We really don't have this. Like, this is the equivalent of like trying to solve for human psychology by looking at like scans of the human brain. This is like really non-trivial problem to solve. And to the best of my knowledge, Lucius is not working on this anymore because he also realizes it's really hard. And yeah, most current mech-interp work, if you like try and run it on causal scrubbing or run it on any kind of real benchmark, you'll realize that it's extremely bad at recovering loss to the kind of like precision that we actually want to back out the kind of explanation that we want. And like you could have like, it's definitely an argument you could make that if you keep scaling up mech-interp work, you will get to this point where you get like 99% like loss recovered or something. But that's also like, well, that's the kind of thing that like takes a lot of work going in. It's also the kind of thing that like could be done much faster, in my opinion. But like, yeah, that's about mech-interp work. Oh yeah, optimistically, the main case for mech-interp work is like, I'm sorry, I made these slides like an hour ago, so I forgot like most of what I put into these slides. So I'm just like going through them and remembering what I wrote down. Like the optimistic case for mech-interp is like, okay, you look at the model that you've just made. You made GPT-6 in your lab, or you made Claude 5 in your lab, and you look at it and like, oh, I see a deception feature here before I start optimizing against an unique capacity. And you're like, okay, cool. I'm gonna like tell everyone about this. I'm gonna shut everything down because like our models are starting to be deceptive. And that's like, sure, that's like one way in which you can go about it. Like, but it's the kind of thing that like definitely isn't very robust. So it's an average case solution that like if you apply any optimization against it, it breaks immediately. And it also works in the kind of worlds where like deception, for instance, the kind of thing that does pop up as like a deception feature within the model. And like that's like one cluster of worlds. Another cluster of worlds is the ones where like deception does arise in these models. It doesn't arise in a way that you can back out easily with a feature. It just like the model chooses to be deceptive as like a consequence of something else, and you can't really like easily detect that in your model. And yeah. This is like, yeah, that's about mech-interp interpret. Any questions so far? I feel like anyone who likes mech-interp would have contentions.
What is the general way like the deception is measured?
I mean, it depends on like exactly how you operationalize it. In as much as I care about like, you know, making AI go well, I care about like the hardest version of this. Basically, any outcome where like AI systems achieve something by humans being deceived in the world, I call deception. Mm-hmm. Some people have more narrow definitions of this, where like an AI actively has to like lie to a human. But like, yeah, my position is basically if an AI system is achieving something because a human is being deceived, I call that deception. That's bad. Yeah. Yeah. Go ahead. Yeah. Actually.
But you know, you say how was it but like how do you like measure that in order to map in terms of the loss of a like in terms of actually measure that and then compare it to the latent space or something.
Yeah, that's the kind of thing that's the kind of like that is hard. Like I don't have a good answer to that. And that's the kind of reason why I say like robustly identifying this kind of thing is really hard, because deception is like it's a property of like the class that belongs to agent plus environment, because it's a property of like a bunch of weird interactions in the environment that lead to the observer being deceived. So like it's the kind of thing that's really hard to come up with like a robust metric for. But like if you want to prevent deception in the fully general sense, that's specifically deception, that's the kind of thing you're gonna have to do. So it's a really hard like conceptual problem to figure out how you're going to interact with that. So like yeah, there are simpler versions of that, but yeah.
In the second cluster of worlds you talk about, like the model just like decides to be deceptive because of like its internal reasoning, that like there's no like deceptive feature that like activates. Do you think that like mechanistic anomaly detection will be able to catch that?
Yeah, I think that like mechanistic anomaly detection, if it works, would like be able to capture the point at which like, well, mechanistic anomaly detection makes one very strong assumption, which like might be reasonable, which is that you definitely have a data set on which your model is safe. Okay, and if you have that, then mechanistic anomaly detection, if you do it properly, by definition, would be able to capture the point at which that mechanism stops being safe. And so like it's sort of a circular definition that you need to solve a really hard problem for what exactly be my mechanism here. But like if you have a system, if you have a data set on which your model is definitely using a safe mechanism, then independently of like what new mechanism it's using, As long as that mechanism isn't something that you would endorse, like then that's bad to you. Like this is mainly irrelevant in as much as you care about intent alignment specifically, because like the mechanism that you're using originally is like something you can say is like nice because like the model's like aware of all of the outcomes that will lead to, like the main if you get a robust intent alignment, it's like a bit of a tangent, but if you get robust intent alignment, your model will never like be deceptive to you, even in like ways that it isn't thinking about. In as much as you can get like deception without your model explicitly thinking about deception, it's because like the model's cognition isn't pointed at preventing you from being deceived, right? So like the model, in some sense, the model is like has the capacity to be aware that its actions are leading to humans being the observer being deceived. It just doesn't really care in some paradigms. So like that is the kind of mechanism that we don't like. We want the kind of mechanism that like leverages the model's own like capability toward exactly what we want it to be pointed at. In this case, us not being deceived, right? So like if it starts using a mechanism where it doesn't really care whether we're deceived or not, that's a mechanism we don't like. And mechanistic anomaly detection by definition should be able to like figure out, okay, this is the mechanism we like, and that's the mechanism we don't like, and we can figure out when it's transition between two. But like that also becomes like a really, really hard problem. But like yeah, if solved, it would be able to do that. Yeah. Any other questions? Okay. Okay. Go ahead.
What do you think of like top-down approaches like circuit distributed?
So like there are some I guess it depends on like how you operationalize top-down, because like there are some approaches to top-down interpretability that I think are really, really exciting. I call what I work on high-level interpretability, which is like literally taken synonymous. So I definitely think that like top-down interpretability is good, but like some approaches to it I think are like still making some of the same mistakes. Like circuit discovery, for instance, still assumes a lot about like linear representations, etc. Representation engineering does a bunch of the same thing. CCS is slightly better in that it doesn't make some of those assumptions, but it still makes like other assumptions and like tries to take a very descriptive standpoint. But yeah, I'd say that like that's definitely like a step in the right direction, even if it's not like, even if it's only like covering a little fraction of the way there. Like there's definitely much more like conceptual ground that could be already covered that like they aren't covering. But like yeah, it's definitely like a step in the right direction, I'd say. Any questions? What's the next one? Oh yeah, latent adversarial training. I'm just gonna like quickly speed run through a few different approaches that like also run into like some of the different problems. So latent adversarial training is, well, how many of you here know what like inner alignment is? Just like as a broad show of hands. Okay, inner alignment is just basically the problem where like you have some training signal and your model ends up optimizing to something slightly different because your reward signal is underspecified, and you like off distribution the model starts doing something entirely different. This is like where all the standard failure modes of deceptive alignment come in. And so like if you want to prevent that, the standard solution is just adversarial training. It's a standard solution to distributional shift. But like in generality, this problem is really hard because there are like some inputs that are like really, really, really hard to find. So for instance, your model could choose to only deceive if it sees like the factorization of RSA 2048 in the wild, which is not an input that you could ever like come up with in the lab. And that's like something that's really, really, really hard to find. So adversarial training would never really find it. So one way to like solve this problem is to like relax. Well, it's called relaxed adversarial training, but instead of like coming up with the factorization of RSA 2048, you come up with what they call a pseudo input, which is like some way to describe the factorization of RSA 2048 without like actually coming up with it and seeing what the model would do then. And like if it makes no sense to you how to do that, good. You're basically in the position I was in 2 years ago. And latent adversarial training is one way in which you can actually do this, where you operationalize pseudo inputs as basically like interventions in the model's latent space, where you just like make edits in the model's latent space to make it believe that it has seen the other factorization of RSA 2048 or something to that effect, and like see what kind of effects that has. So that's a much more tractable thing to like observe. And like so this is the kind of thing that's like really, really exciting as an approach, because then you do get to like solve a bunch of problems with like in theory, you get to solve a bunch of problems with like inner alignment, and because you get to do like actual adversarial training that's like really, really solid. But in practice, when you try to do LAT, you run into the problem that like you really, really easily get degenerate outputs. And what I mean by that is you're generally doing LAT to say, here is the reward signal, and you're trying to like come up with a way to edit your model's latent space such that it performs really, really badly on the reward signal. The intuition here being that like if your model is deceptive and you trigger some kind of input and it starts being deceptive, it's going to like act in a way that's like at odds with the reward signal you gave it. The problem here is that like there are many, many ways in which you can edit your model's latent space such that like it does perform really badly in a way that like isn't very interesting. Like if you do this on a language model, you can just start outputting random gibberish and it'll just like perform really, really badly on the next token prediction loss. That's definitely a thing that can happen. So if you want like, So ideally the thing you'd want is a way to make edits in a way that's really much more principled than this. Like, you want to make edits in a way that like directly corresponds to like interesting behavior in the model. There's some conjecture that like SAEs will get you some of the way here. There's some conjecture that like you can simply apply KL penalties and get out of the way. But like in general, like yeah, these prosaic approaches definitely do work to some extent. Like that's one of the things I'm working on to figure out whether like applying a KL penalty against like another language model like get you some of the way because you won't get gibberish at least. But like the principal way to solve this would be like figure out like how do you make edits in a way that like such that your edits directly map onto like interesting behavior from the model. And that also comes around to what is the right ontology to operate in / like how do you figure out how to translate the things you care about into the model's ontology. This is a common recurring theme that will come around later again. CCS. How many of you here know what CCS is? Okay. CCS is Colin Burns' contrast consistent search. And if you heard Oliver Haprika's talk today morning, he does not like CCS. I also think CCS is pretty bad, and I think this should have been completely obvious in retrospect. Where CCS takes basically like, here is one property that like we think truth representation systems will always have, where the property is like you train a linear probe such that what was it? It's always going to represent. You take two sentences, one of which is true and one of which is false, and then you train a probe such that like the probe score for one of the statements is always 1 minus the other, and such that the minimum of one of the two is always like 0 or something like that. And you try and like take these probes and see how well you can extract latent knowledge out of them. I think this is a great approach, to be clear. I think this is definitely the kind of thing you should be doing. You should be like taking things you care about, like truth representations, and coming up with properties that extract them in arbitrary systems and like see how much you can get out of them. The problem with CCS is that they took one property and tried to figure out exactly how much you could get out of it, and it doesn't work. And it doesn't work for so many reasons. As Oliver said, it didn't have like bunch of people tried to replicate it. It didn't really replicate very well. DeepMind alignment team tried to spend a bunch of time trying to figure out like whether to generalize or replicate. They also discovered that it doesn't really work or generalize in any capacity. And the problem here is that like you really shouldn't be trying to do the kind of thing where you like take one property and like spend months of work trying to figure out like how much you can get out of this one property. That's like not the way you should be like doing this kind of science. It doesn't replicate very well, doesn't generalize. Yeah, it definitely has the right spirit in that this is the kind of work you should be doing. But the kind of thing you really should be doing even more than that is you come up with one property, you spend like a little amount of time, see how much you can get out of it, and it's definitely non-trivial capacity. CCS isn't like completely trivial. It does work in like some settings. But the thing you should be doing is once you realize how much you can get out of one property, you spend more time coming up with like more property and flush out the operationalization of truth representation that you do have. Like don't stop by saying, this one property implicitly defines truth representations everywhere. And then you then come up with like more and more ways to like figure out in what context the property you came up with breaks. Like eliciting data knowledge, which is Paul Christiano's original report, does this interesting thing where like one person suggests like here is one way in which you can like structure a training process such that you'll always get like models to answer questions honestly because of some simplicity prior or something. The other person says, but in this context that'll break. And then the other person suggests like another thing that like could work, and then the other person breaks it again, and so on and so on and so on. My general answer to CCS is that if it was proposed in the ELK document, it would have taken like 5 minutes for someone to come up with a context in which that doesn't work. And like yeah, that's basically like how it works in practice. Like people underestimate the extent to which like thinking about worst case alignment guarantees like does actually give you like predictive power over how well things will work in the real world. But like yeah, definitely the right spirit, and the thing you want to do is flesh out operationalizations of truth representations. But yeah, CCS is good, but it could be like significantly better. Yeah, unlearning is another one, also really hard to get right because trying to draw a conceptual boundary that makes sense to us in a different ontology. Standard thing here is like trying to erase a model's knowledge of like Harry Potter, and you can try to do this. Like there are some approaches that do this like fairly well. There was a Microsoft research paper from a couple of months ago that tried to do this and like said they got like really good performance. Then you prompt the model for like a dark-haired boy going to a wizarding school or something, and it'll tell you basically the plot of Harry Potter. So like you want to draw a conceptual boundary around something that's like a really arbitrary one if you like view it from a completely different ontology, and like you again come to the problem that your reward signal is always going to be underspecified. The thing you're trying to get out is going to be underspecified because you can't figure out like what a fully general version of it is. And historical unlearning methods are also like they're not very robust. Like you try to do the Harry Potter thing, it doesn't work. Even if you try to do latent adversarial training to remove it, it's like also really hard because the problem here is that you're not specifying really robustly what it is that you want to remove. And yeah, if you prompt in indirect ways, which is basically what the Harry Potter thing happens. Rome is like another approach, which is like before CCS's time, where like rank one model editing, where you try to like remove this is the thing I talked earlier about, like editing a model's like latent knowledge to like say the Eiffel Tower is in Rome, and you get like 40% erasure. I tried to find this exact statistic somewhere, but like I couldn't find it. But from what I remember, it's like 40% erasure that you get in the model when you try to like make some very strong assumptions about locality and like locality of knowledge representation. And it's the kind of thing, like every 6 months, if you're in alignment, you'll see this thing happen again and again, where every 6 months someone will come up with some alignment research agenda that sounds very, very exciting to a bunch of people, because they always like, oh wow, we got like 60% model steerability or model erasure or like 60% recoverability of like loss on this one thing from this exciting new technique. And then you try it on like literally any other context and it doesn't work, because you really shouldn't be measuring these things in terms of like linear percentages. You should be much more representing them in terms of bits. 40% erasure is like less than 1 bit of like actual erasure. You want something that's much more robust than this. Like it's been Rome, and then since after that CCS, after that activation steering, and then like every 6 months someone new will come up with something that like has a roughly 40 to 60% every single time, and then basically doesn't get much beyond that, because like the last 9s are the things that are like much harder to get. And the overall idea here is just that like, yeah, if you want to do any of these approaches properly, you want them that actually robustly tries to identify things that you care about. And none of these approaches try to do that, which is why they all just like don't really work very well, and which is why presumably none of you have ever heard of, many of you have never heard of them before, because like they don't really work very well. They don't really stand up very well to the test of time. I will be going on a bit to like what I'm working on, but any questions so far? No questions?
In the lab I'm working in, they did some like before me they did some research on trying to find like fully invariant paths throughout the parameter space that kept some property like except like for example the global loss on training set constant while changing some other parameter to whatever they want, right? And like they were able to like get like they were, for example, one property they wanted to change was like how like the main purpose of this was for continual learning, like so they basically because they to basically deal with forgetting, and they managed to like improve, they keep basically total loss constant like for the previous data set while improving on other data sets. Do you think that could be applied to like things like unlearning, where you like instead of trying to keeping total loss more or less constant with chain set, but then the maybe increasing loss for like Harry Potter or something?
Yeah, that makes sense. Actually, it's like somewhat similar to like what Rome tried to do, that they also try to come up with like causal pathways within the model to like edit stuff. But like, yeah, I expect that like it'll be really hard. But like, yeah, that's definitely the kind of like research direction I'd be like very interested to see what comes out. Yeah, I expect it'll be like really hard to get out like stuff that's very interesting. I expect that like on priors, I'd say there's like some kind of degenerate outcome you're drawn into, and then you like slowly incrementally build up like better and better things. Mm-hmm. But like, yeah, it's definitely the kind of research direction that like it's like the kind of thing that like it works ambitiously, which is generally kind of interpretability work alike. So like, yeah, my general answer. Any other questions?
Do you have like suggestions for better like metrics then, like instead of like percent erasure?
Yeah, I mean the obvious one is just like how many bits of like if you translate it into like well, it's a very very hacky one, but like very informally as used, like how many bits does this correspond to? So like if you get like 90% like erasure or something, that's like what, like 3 bits or something, and like ideally you want a kind of thing that's like infinitely robust, or like you had to answer some questions about like how many bits you want. But, like informally, that's the one I use. You could also like use. You could still use percentages, but then you have to answer some questions about like how confident are you that like this much percentage captures most of the things that you care about. Like I was talking about earlier, like less than 98% would capture like GPT 3.5 performance and GPT 4. But if you capture 99%, you can make the claim that like this does capture most of the difference between GPT 3.5 and GPT 4. So that's all we're interested in. So even using percentages, you can still make claims like this. You just have to like make sure that you're arguing about the right thing. You should make sure you're like confident in your claims then. Yeah. Any other questions? Also, feel free to ask like if you want me to like explain something because I like brushed over it too quickly, or you want to say like this makes 0 sense why you believe this and it feels like very strongly claimed, or like I didn't understand this, could you say it again, or like this is way too fast, or basically anything. Any comments?
When you say the Rome has like 40% erasure, because Rome is used for model and like editing them.
Oh yeah, probably used a different word. I think Okay, so the thing is, I remember reading this comment from like a year ago, but I remember someone saying, Rome works like 40% something. And I spent like basically 4 hours yesterday trying to dig down this one comment, and I couldn't, and I gave up. But I remember the word 40% strongly associated with Rome. I'm pretty sure it was Paul Cristiano that said it, but I couldn't find this comment. But like, yeah, 40% something Rome works. And I wrote down the word erasure like 20 minutes before the talk started. It's like, yeah, Rome works 40%, etc., etc. Yeah. Something like that. 40% robustness of edits or something. Like it works 40% of the time, maybe, like approximately. And like if you prompt across a bunch of different instances, it works 40% of the time. There are also a bunch of different problems with Rome, like bidirectionality and like general robustness, etc., and like over optimization, stuff like that. But like, yeah, works 40% of the time is probably a good. Ignore the word erasure. Yeah. Any other questions? Cool. What time is it? How far have I been in?
Yeah, I think you got like 30 minutes left or so.
Okay, cool. Okay. This I'll just go through very quickly because it's basically borrowed very heavily from like Evan Hubinger's Interpretability tech tree post. I like that post. I think there are some very minor edits that I'd like to make, which is why I like very quickly included it here. Evan Hubinger's tech tree basically follows like 7 different kinds of like interpretability, where he calls like best case interpretability, worst case interpretability, training process interpretability, like model interpretability, architectural interpretability, etc., etc. I'm just going to like modify them a bit and talk about like some different framings I like to use for interpretability methods. Low-level interpretability, being able to understand like specific individual local components of models. This is basically what most current mechanistic interpretability tries to do. Like look at an attention head, say what does this do? And if you can do this while recovering like 99% of what that attention head is doing, I'd say yeah, this is a great example of low-level interpretability. A lot of what Anthropic's work is doing definitely tries to build toward this. I don't think they're like doing it as fast as they as targetedly as they could be doing, but like it's definitely like kind of approach that's like very good low-level interpretability work, like trying to look at local components of the model and trying to understand what they do. In Evan Hubinger's tech tree, this is referred to as like best case interpretability. Okay. High-level interpretability is basically being able to robustly interface the component that may be present anywhere in the system. So basically, if you like expect deception to be present somewhere in your system, you don't want to like only look at like specific components and say, okay, this is indeceptive. Also, this other thing is indeceptive, and then replicate that for a trillion parameter model. You want to be able to like search over your model completely for deception that may be present anywhere in whatever way you think deception might be represented. So that's basically what high-level interpretability is. In Evan Hubinger's tech tree, that's referred to as worst case interpretability. And the reason I don't like these terms is because there's another phrase, there's another place in which I like to use the term worst case interpretability, which is to contrast it with average case interpretability, which I talked about earlier, where average case interpretability is a kind of interpretability solution that works on a model if you like don't apply any optimization pressure against your against your interpretability tools. Because like if you apply optimization against your interpretability tools, you will like give the model a really, really strong pressure to hide its deception or whatever it is. Like if you search for deception in a very like prosaic way and you train against that interpretability tool, try and hope that like you remove deception in your model. One obvious thing that will happen is the deception goes into the part of the model that you're not looking at. So that's the kind of like problem that happens if you like try and train against your optimization tool. So like another two different kinds of interpretability is like average case versus the other worst case interpretability, which is like the kind of interpretability tool that like just works. And like most of Anthropic's theory of change is basically average case interpretability on like one cluster of failure modes. But the kind of interpretability you'd want ideally is the kind of like that is actually robust to optimization pressure, so that you can train against it and get the kind of like model that just straight up like doesn't have the kind of things you're worried about. And now high-level interpretability. I just like, I could talk for like 30. I'll just talk about this very briefly, honestly. I have like 10 more slides after this, but like I didn't like calibrate how long it would take me to cover the rest. I'll just cover this very briefly. This is basically what I work on. Well, that's a long definition, but I'm going to read it out anyway. Identify a robust and generalizable specification of high-level properties in the real world relevant to safety, such as objectives, and target their high-level structural analogs in the neural net. And I copied this definition from a talk I gave like a month ago, so I'm reading this definition for the first time, reading how clunky it is. But the idea here is like basically that you just, thank you, yes. The idea here is basically that, yeah, if in as much as you care about like what specific parts of your model you want to explain, I mostly focus on objectives, and by objectives I generally mean targets of internal optimization or internal search that's happening inside the model, and figure out like how do you come up with like a robust and generalizable specification of this thing, of an objective structure, such that given any system you can like search over it to find this objective structure and then translate it to like human understandable form in the real world. And in practice, it basically looks like, in practice it basically looks like that. It comes up with more and more properties that flesh out your operationalization of what you mean by objective structures. Ideally, you'd come up with something necessarily and sufficiently describes objective structures, and then interpreting those the structures that like have those properties within the system. So to draw an analog to causal scrubbing basically tries to come up with like a sufficient description, sufficient explanation for like some kind of interpretability hypothesis. And like that's why the trivial solution to causal scrubbing is basically saying, the entire network is doing this. And when you try to do like high-level interpretability, like when you try to do CCS or Rome or the kind of work I do, this is basically the kind of thing you get. You get a strict superset of the things you care about. But that's why like it's really important to come up with the kind of thing that like also necessarily describes the things you care about. Like you want to focus on a very, very strict subset of your network that like captures all of the relevant properties that you care about, and then figure out like exactly what things in the real world that maps onto. This is definitely like a low-level interpretability problem, but I consider this to be like the hard part of it, where you like interface with a very specific part of your system, such that like regardless of what you do, how much you optimize against it, your system will always contain like you'll always be able to extract objectives by looking for things that have these properties in the system. And I think that's it. This is like some specific things that I did earlier, but like that'll take a while to get into, and I'd much rather like answer questions now. I think that's like most of the content of my talk, so I'm just open to taking questions now. Any questions?
Could you like explain a little bit more about like the point of like addressing deep deceptiveness as a different case of just regular deception, just like for the people who like might not have read?
So the problem with deep deception is like I'll just like flesh out what I'm that example a bit more, because I feel like I rushed it over. So let's imagine you have a model that, Evan Hubinger has this idea that like what he calls precursors to deception, such that like these are the things that have to be mechanistically present inside your model, such that if it's going to be deceptive, it's going to exhibit these properties beforehand. Like obvious ones being like agency or non-myopia, this and the ability to plan along long time horizons, etc., etc. And one way in which you can prevent like deception, explicit deceptive cognition arising in your network is to like train against these precursors to deception and ensure that your model is never explicitly thinking about how to deceive humans. Like this is definitely a thing that like you can do with much better interpretability tools, even just like much better versions of current interpretability tools. And then you get this kind of thing. So you have a model that like you're really, really, really certain is never thinking about how to deceive you. And then you train it like output protein recipes and send them to a wet lab, along with some explanations of why these protein recipes are safe to run. And they have some manual human raters who like look over these explanations really quickly. And if they think of any of them as sus, they send them to like a human expert board that reviews them for weeks. And then you optimize the model to like get past the review process pretty quickly. And since the model cannot be think deceptive thoughts, you're like, oh, this is safe, because the model is never going to like think, okay, how can I construct explanations such that like it gets past the review process quickly? But the model is still like a really competent generalist agent, so it still can like search through different cognitive strategies in the real world. In a very trivial sense, you can imagine it like brute force searching through a bunch of different plans in the real world, such that it eventually stumbles across one that looks like output explanations that look like this one very specific thing, right? And this gets you a bunch of really good performance for some reason. And like it doesn't obviously have to look like that. In the realistic case, it probably more look like iterating through like a bunch of different cognitive strategies itself, like a bunch of different ways it can think about the real world, such that like it ends up thinking about what are the bottlenecks exactly to me having higher performance here, and then it runs up against a wall every time it starts thinking about like how to model human psychology, and then like it pauses there and then goes back and eventually keeps running up against that wall and finds a way to like think in a way that like gets past this wall without explicitly thinking about deceptive cognition. That's like a bit hand wavy, but like that is a good post that goes into this in more detail called Deep Deceptiveness, or my own post, Thoughts on Solving Deep Deception. But like the idea here is that like it's pretty possible, especially if you like actively optimize for it. It's very easy to come up with an agent that has that like is just competent in the real world without like having whatever property that like is sort of a proxy to that. Like explicitly thinking deceptive thought is a proxy for having the consequence of deception in the real world. And if you apply active optimization against this proxy, that proxy breaks. And active optimization can be applied by an agent just trying a bunch of different things in the real world, especially if you don't like punish it for like trying and failing, which is really hard to do in practice. So if you try to do that, then your agent will be able to come up with explanations that like pass the review board process very easily and quickly, but the protein recipes themselves aren't very safe, and then it just like goes through and just like has a bunch of chaos and like havoc and etc. etc. So like yeah, the idea here being that like the thing you're really worried about is mistargeted optimization, and another source of mistargeted optimization is the model acting in the real world on unbounded timescales. And that's like deep deception. And like the way you solve this is like by pointing the model's own cognition and explicitly preventing you from being deceived, which is why you want intent alignment, which is why you want to be able to steer the model's own internal mechanistic objectives, which is why I work on high-level interpretability, etc., etc. So, any other questions?
Well, did the session end at 6:15 or 6:30? I forget. Do you have a little more time for questions? 6:30? Okay, perfect. Yeah. So yeah, continue.
Go ahead.
Can you talk a little bit more about intent alignment and what that like looks like?
Yeah. So intent alignment basically, Paul Krishna came up with the term. I think it may have existed before, but it's basically like robust like value alignment, where like you actually manage to create an agent that has the exact same values that you do. In a way that like, there's some nuance there around what it needs to have the same values that you do, but it's basically like, this is what RLHF tries to do right now, where RLHF tries to like give behavioral feedback in a way that like, creates a model that has the values that you want instilled into the RLHF reward model. But RLHF is not very good at this for a bunch of reasons. But yeah, this is like, intent alignment is basically whatever it takes to create an agent that has the exact same values as you do. And like that's obviously a really, really hard problem for a bunch of different reasons. But like, yeah, that is the target, I suppose. Like, do you have any more specific questions there?
Yeah. So like, if an agent is intent aligned with you, it might like in order to not deceive you in its actions, it might have to like think about how to not deceive you, and thus think about what a deceptive agent might behave like in its thoughts, right?
Yeah.
So there's like a kind of incompatibility.
Yeah, and that's exactly the kind of reason why like standard mech-interp that just looks like, is there a deceptive feature here, I think isn't really a good way to approach this. Because like even in cases that aren't that, but even in a case where like an agent is trying to model whether other agents in the real world might be deceptive, you'll still get like deceptive features within the model. And so you need to like figure out how to properly contextualize those. So like, yeah, this is definitely one of the reasons why like simply looking at like basic deceptive features from the model doesn't exactly get you what you want. I need to figure out like exactly what level of abstraction do you want explanation of your model to operate on, and like standard like extremely low level interpretability will just get you a very very broad and sparse explanation that just like doesn't capture like everything you want at the right level of abstraction, and you can run into exactly those kinds of problems. Yeah, you want a kind of thing that like tells you, okay, it is thinking about like how to deceive humans, but for the exact explicit purpose of not doing that. You want a kind of explanation that captures that kind of nuance as well. Yeah, and that's why it's really hard, and that's why low level interpretability is not something I'm like that excited about.
Do you think combinations of like 60% explainability approaches can, approach a 98% explainability approach?
Combinations of what?
Like 60% explainability approaches.
Yeah.
Like, if you have an ensemble of those, does that work?
Maybe. I mean, I expect that like there's. This is definitely like untested intuitions that I have, but like I expect that like an ensemble of different approaches that people come up with in the short term, I expect them to capture like a lot of low-hanging fruit about the model, such that like a lot of the 60% they capture is like bunch correlated with each other. Like it's definitely possible if you like combine like 10 different approaches, you get like to 98%. And in some sense, that's like also what I'm trying to do. And then I'm also trying to come up with like specific properties that I'm trying to leverage that capture like increasing parts of the model that I care about, and like hone in on like specific parts that I care about even more. But like, yeah, I expect that people who aren't explicitly thinking about how to like come up with things that capture different things that have been captured before will just capture a bunch of correlated information. So they'll still keep getting incremental progress, to be clear. But like it then becomes a question of like how quickly are you making incremental progress such that like you can like get stuff that works in time. Yes. Any questions? Yeah.
As like the model scale, have you seen any like issues with like some like interpretability tools like working at smaller scales, but not working at larger scales, or the reverse where they work at larger scales but not smaller scales?
I feel like there has been prior work on this. I don't remember anything off the top of my head. I feel like maybe one trivial example that isn't exactly what you're talking about is just like interpretability tools that like worked on really small models, because like really small models don't exhibit superposition really well, and then like larger models exhibit them much more strongly, and then you run into a bunch of problems there. There probably has been other work like measuring interpretability tools on like larger versus smaller models. I don't remember any of that off the top of my head though. Like, yeah. Actually, maybe there haven't been. I feel like if there were, they'd come from Anthropic, and I can't remember any Anthropic paper that does this. But like, yeah, then maybe there's like some paper that does this like small versus even smaller models. But like, yeah, I don't remember anything off the top of my head. Any other questions? Go ahead.
Could you explain like what the success story looks like after this? Because like at some point you will need to like come up with some kind of like definition of the objective that you want. So like
Yeah.
I remember like you talked about like RLHF on like the direct objective or something like that.
Yeah. So I mean, like, the really, really ambitious version of this is like you actually do come up with a list of properties that necessarily and sufficiently describe objectives, and then like, well, one hacky version of the ideal version of this is that like you train a probe to identify structures that have all of these properties, ideally like a nonlinear probe or something, and then you like that you can claim that like if you're really confident that you've identified the necessary and sufficient properties, then you can say, okay, whatever structure it is that I've identified, that then is the objective structure, and then you solve the problem. Then you just like do low-level interpretability to figure out what those map onto, and then you do RLHF on that. Like that is a different problem here of like what exactly you mean by translating that thing. But like the ambitious, like maybe like a hand wavy picture here is like, a really, really hand wavy picture. Come up with like a general mathematical formulation of what you mean by an objective structure in any given system. Search over that mathematical formulation in the system that you have. Then figure out what things in the real world that mathematical structure corresponds to, and then like steer that toward like whatever you want. That's like really handy. I can get like more in detail on any of the specifics if anyone's interested. Any other questions?
Then maybe a follow-up to that would be like, what would the success story look like if we only get a hold of like what deceptiveness looks like including deep deceptiveness?
I mean, I expect that like, so the word only is like someone throwing me off because I expect that deception to be like strictly harder than objectives for a couple of reasons. Mainly because deception is like a property of agent plus environment, and objectives is like fortunately just a property of agent itself. But like, yeah, this is definitely something you can do with like deception. I expect it to be like also look like something similar, where you try to come up with like a generalizable mathematical specification of what it means to like have something that like is deception in like a mathematical model of an environment, and then you could like search for that in like the system that is the agent plus the environment or something, or just like come up with like a subset of that, like search over it in the model itself, or like search over like things in the model that lead to these outcomes in some model of the real world. But like it's definitely much more complicated to think about. And I have an entire post that goes into, I have no idea what like trying to solve for that would look like. But yeah, go on.
Would looking for deception be different than looking for intention to deceive? Because like if intention to deceive.
Yeah, that's well, it depends on what you mean by intention. That's explicit intent, which is like, yeah, the model explicitly thinking about it. That's much easier to think about. There's also like implicit deception, which is that the model achieves some task because its actions have the consequence of deception. And like, I'm also worried about those things. There are definitely people who are only worried about like in explicit deception, and so they think the problem is easier. But like, in as much as I care about like untargeted optimization and like just generally making AI go well, I'm also worried about like this other kind of things. Like, yeah, expect that if you only focus on the first thing and you fully erase that, by default you just get the latter. So like, yeah, that's mostly what I think about. Like, I do think about like explicit optimization, explicit deception as being easy, but I worry that if you focus on it and remove it, you just get implicit deception. So yeah, that's probably what I say. Any other questions? Go for it.
One more would be like, do any of these like plans change as like timelines shorten, or like is just the work we'll have to do regardless? So let's just try to do it as fast.
So it's definitely like I feel like I feel like 6 months ago I would have said that one of the things I like about my research agenda is that because you're coming up with more and more properties over time. Like right now with the work I've done, I have something that's definitely not robust at all, but that like gets you some amount of steerability in a model. So I'd say that like, yeah, you can definitely use this today and you won't get something very, very good, but you'll get something that's like better than nothing. Now I'd say that like, I don't know, if timelines were like 2 months, I'd probably say every alignment researcher in the world should stop everything they're doing and just all go work on Redwood Research's AI control agenda or something. And if timelines were like 2 years, I'd probably say like everyone should just do like MECINTERP and just pray that alignment turns out to be easy. If it was 5 years, I'd probably say do this. If it was like 5 years and more, I'd probably say that like do this as a median. Like I think that it'll take like 2 to 5, maybe less than 5 years. I'd say probably like take like 2 to 5 years for something like this to become something that's like strictly better than every other method in existence. Like this or natural abstractions or mechanistic anomaly detection, I'd say like it'll take at least in the order of 2 to 5 years for any of them to become better than like everything else in existence. But like I do expect it to reach that at some point. But if like timelines are shorter than that, then I expect everyone should just work on like something else and hope to God that we survive. Yeah. Any other questions?
Sounds like we end on that note.
Awesome.
Okay, cool.
Thank you guys.